I welcome you all in this lecture on scattering matrices and properties of scattering matrix. Where in the previous lecture, we have seen the advantages of S parameters over the other parameters like ABCD parameters, Z parameters, or Y parameters. In this lecture, we'll try to find the relationship between incident and reflected waves in terms of S parameters. For example, we have an N-port network shown here. In the figure, we have an N-port network. Now, what we are trying to do is that we'll try to see the relationship between an incident wave and a reflected wave. Likewise, at all ports, we'll be having an incident wave and a reflected wave. I am designating the incident wave in pink color and the reflected wave in red color. Likewise, at port 3 we'll be having an incident wave and a reflected wave, and eventually at port N we'll be having an incident wave and a reflected wave. So our aim is to find the relationship between these incident and reflected waves, relationship between incident and reflected waves in terms of S parameters. S parameters. Now let's look at port 1. We have the incident wave. We designate it by A1 and the reflected one wave by B1. At port 2 likewise we'll have an incident wave A2 and the reflected wave as B2. At port 3 we have incident as A3, reflected wave as B3. At port N we have incident wave as AN and reflected wave as Bn. So An corresponds to incident wave and Bn corresponds to reflected wave. So what are these waves? These are basically voltage or current waves. In general, for an ith port, for example, I have an ith port here. Ai would correspond, let me use another color. This is, say for example, our ith port. Let me use this. This is our ith port. So if this is our port number I, AI would correspond to the incident wave in general and BI would correspond to a reflected wave BI. So how do we relate these incident and reflected waves to, for example, voltages or currents? I'll use an expression. Say AI is basically VI positive by root of ZOI and BI is equal to VI negative by root of ZOI, where your ZOI is the impedance or the characteristic impedance of port I. So what is VI positive and VI negative? VI positive is the amplitude of the incident voltage wave on the ith port. and Vi negative is the amplitude of the reflected wave. At ith port. So this AI and BI, these are the this is AI is then the normalized incident wave, normalized incident wave, and BI is normalized reflected wave. Well, in terms of currents, I can write these as I positive into root of ZOI, and BI can be written in terms of current wave as I neg root of ZOI. Now if I square these quantities, before I square it, let me erase this. See, now I have voltages, the incident wave as AI and the reflected wave as BI. Now what if I square these quantities? Say for example I square AI square, I'll also square the quantity BI square. AI square would be Vi positive square divided by ZOI. So Vi positive, as I said, it is the amplitude of the voltage wave. So Bi square would be Vi negative whole square by ZOI. So which in turn means that if I divide these quantities by 2, for example AI square by 2 would now be Vi square by 2 ZOI, implies AI square by 2 is Vi positive by root 2 whole square divided by ZOI. Now what is Vi positive by root 2? Vi positive, as I said, it is the peak of the voltage wave. So Vi positive by root 2 would mean the RMS value of the voltage. So if I square Vrms square by ZOI, so what is this quantity called as? If I have Vrms square by ZOI, this means this is the power. So this is basically the power. AI square by 2 basically is the power corresponding to the incident wave. So likewise, Bi square by 2 would be Vi negative by 2 ZOI. So this would mean basically Vrms by ZOI, Vrms square by ZOI. So that means this is the power which corresponds to the reflected wave. So Vrms square by ZOI or Vrms square by characteristic impedance is basically the power. So AI square by 2 corresponds to incident power, and Bi square by 2 corresponds to the reflected wave power. So in general, power absorbed by ith port is equal to AI square by 2 minus Bi square by 2, where AI square by 2 corresponds to incident power, and this corresponds to Bi square by 2 corresponds to reflected power. So this is the average power, basically average power absorbed by the ith port, as we have used the equation of Vrms square by R. Vrms square by impedance in general corresponds to the average power. It is worth to mention here that it is the average power that has a physical significance. Average power has a physical significance. The RMS power that we sometimes use has no useful meaning. RMS power has no useful meaning. Has no useful meaning or physical significance. It's no useful meaning or physical significance other than being a quantity that can be calculated as an exercise. Further, for TEM modes, the incident and reflected voltage waves can be the actual waves, voltage waves, but for non-TEM modes, V is defined as proportional to transverse electric field. And I there is defined as proportional to transverse H field. For deriving the relationship between incident and reflected waves, we could have even used, for example, we could have, instead of AI and BI, we could have used, VI positive and VI negative directly. VI positive and VI negative. Let me use a different color. We could have used an incident wave like VI positive as an incident wave, and for example VI negative as a reflected wave. So instead of AI and BI, all I am saying is that instead of AI and BI, I could have written VI positive and VI negative. But using AI and BI gives us generalized S parameters. This gives us generalized S parameters, as it includes the port impedances as well. Because I said AI is VI positive by root of ZOI and BI is VI negative by root of ZOI, where AI corresponds to the incident wave, BI corresponds to the reflected wave, but it takes into care the port impedances. So this makes S parameters more general. So when we are discussing the relationship in terms of AI and BI, we have a generalized set of S parameters. As in general, in the port impedances, at different ports, the port impedances at different ports will be different. So it is better to use AI and BI instead of VI positive and VI negative. So to derive a relationship between the incident and reflected waves, we'll consider a junction made up of n transmission lines, as for example shown in figure here. So we have n transmission lines. Let this be the first transmission line. This is line number 1. This is, say, for example, line number 2. This is, for example, the line number n. Let this be line I, or the I transmission line. So we have a junction made up of n transmission lines. So at line number 1 I have A1 as the incident wave, and then I have B1 as the reflected wave. This is our reflected wave, this is our incident wave. Likewise at line 2 I'll be having an incident wave and a reflected wave. A2 as the incident wave and B2 as the reflected wave. At the nth line I'll be having AN as the incident wave, BN will correspond to the reflected wave. BN, sorry, I will use red color for the reflected wave. BN as the reflected wave. And this line so far is concerned is my ith line. So at ith line I'll be having AI as the incident wave, and this is my incident wave, and this would be my incident wave, and this would be my reflected wave at the ith port. So what I assume is that I'm assuming that I'm connecting a source at ith port, and I'm connecting loads. Say for example, load at line number 1 is ZL1, load at line number 2 is ZL2, so on. Load at nth line is ZLN. So in order to obtain the relationship between scattering matrix or S parameters and the incident and reflected waves, I'll consider two special cases. Case number 1. The load that's connected to line 1 is not equal to the characteristic impedance of the transmission line, and all other loads, they are equal to the characteristic impedance. That means all ports except the first port here, they are all terminated at characteristic impedances. Since line 2 so on up to line n, they are connected at characteristic impedances, so there won't be any reflections, no reflections. From these lines, from line number 2 to line number n, for example, there won't be any reflections. Reflections would be only because of line number 1. As we know from transmission line theory, if we have a line which is terminated at some load ZL, and if Z0 is the characteristic impedance of the transmission line, if Z0 is equal to ZL, then there are no reflections. But if Z0 is not equal to ZL, there will be reflections. So that's what happens here. So here B2 would be 0 because it is terminated at characteristic impedance. There won't be any reflections here, no reflections. Likewise, there won't be any reflections from line number 2, 3 up to n. So B2 would be 0 up to Bn. So B1 in this case, the first line, which is terminated at a load which is not equal to characteristic impedance, so B1 would not be equal to 0. So in nutshell, what we have seen is that in this special case, B1 is not equal to 0, rest B2, B3, so on up to Bn is equal to 0, as they are terminated at characteristic impedances. So if we look at the junction here, what happens is that B2 is 0, Bn is 0 except for B1. So in this case, we see whatever comes from this reflection goes to this source back. So Bi is equal to B1. And what is B1? B1 basically, if we look here, if we look at this port 1 here, if we look at this port 1 here, what's B1? B1 is basically related to A1. B1 is the reflected wave, A1 is the incident wave at port 1. A1 corresponds to incident wave, B1 corresponds to reflected wave. So B1 is the reflected wave, A1 is the incident wave. They are reflected by something. Let me designate that by SI1. So this is basically reflection coefficient then. Reflection coefficient. Because reflected wave is related to this incident wave A1 by some constant, which is the reflection coefficient. So B1 is reflection coefficient times A1. So we have B1 is SI1 A1. So SI1, so far as the subscripts here I and 1 are concerned, this means that reflections are from port 1 when the source is connected at the ith port. So we have connected the source at the ith port. As you can see, we have connected the source at the ith port, and the reflections are from load connected to port 1. So we designate it by SI1. 1 standing for reflections coming from port 1, I stands for the source is connected at the ith port. So the relationship that we have obtained is that B1 is SI1 A1, and B1 is nothing but BI, as we have seen that BI is equal to B1. So this implies that BI is equal to SI1 A1. So this is what we have obtained. So this is the first case. Now let us discuss another case. So let me raise it first. Before we discuss case 2, let me raise it. So case number 2. So in this case, we'll assume that all n-1 liners are terminated on impedances other than Z0. That is Z0, that is ZL1 or load impedance at port 1, load impedance at port 2, load impedance at port 3, none, so on up to port impedance at nth port. They are not equal to the characteristic impedance. So if I connect here at port 1, I am connecting ZL1. This is our port 1. So line 2, port number 2 is ZL2, and so on. Line number n is connected to load ZLN, and none of these loads is equal to characteristic impedance Z0. So what that means is that there will be reflections from all these loads. That means if I have an incident wave here as A1, B1 is the reflected wave then, and B1 this case would be non-zero. Likewise, A2 is the incident wave, B2 would be the reflected wave. So B2 would correspond to a reflected wave, and in this case B2 won't be equal to 0. Likewise, at nth port, AN, which is the corresponds to the incident wave, and BN corresponds to reflected wave. So that would mean B1 is not equal to 0, B2 is not equal to 0, so on up to Bn. So in this case, Bi would simply be equal to, if we look at this node, you see Bi simply would be equal to B1 plus b2 plus so on bn, b1 plus b2 plus so on till bn. Now what is b1? This is the general expression. So the wave that comes at ith port is summation of all the reflected waves from port 1 to port n. Here, as you know, I can be any of the lines. I is, in this case, I is the ith line to which the source is connected, and I can vary from 1 to n. Now if I vary I from 1 to n, so we'll be getting a set of equations like b1 would be si1a1. Here the reflected wave b1 is related to a1 by si1a1, as we have already seen. Likewise b2, the reflected wave at port 2, b2 would be si2a2, so on till bn equal to sin an. This bn is related to an by sin, where sin stands for the reflections occurring at port n when the source is connected at port I. So this equation, if I name it as equation 1, I can rewrite equation 1 as bi is equal to, instead of b1 I can write si1 a1 plus, instead of b2 I can write si2 a2 from here, so on. Instead of writing bn I can write sin an. So this represents a general equation. Here I, so far is concerned, I varies from 1 to n. So let me move to another page. So let me write this equation as the equation that we obtained is bi is equal to si1 a1 plus si2 a2 plus si3 a3 plus so on up to sin an. As I said, I varies from 1 to n. Therefore I can write it as b1 is equal to, I am replacing I by 1, s11 a1 plus s12 a2 plus s13 a3 plus so on up to s1 and an. If I replace I by 2, I'll get b2 as s21 a1 s22 a2 s23 a3 plus so on up to s2 and an. Likewise my nth reflected wave bn would be, I'm replacing I by n here, so it will be sn1 a1 plus sn2 a2 plus sn3 a3 plus so on up to sn and an. So I can write this in matrix form as, in matrix form I can write it as, I'll write it on the next page in matrix form. This set of equations can be written in the matrix form as b1 b2 so on up to bn is equal to s11 s12 so on up to s1 and s21 S2 to so on up to S2n. The last row can be written as Sn1, Sn2, so on up to Snn. And then I can write A1, A2, so on up to An. So this is basically a column matrix. This is again a column matrix. And we have a square matrix, which is nothing but a scattering matrix. Of order n cross n. So I can write it as B is S into A, where B corresponds to reflected waves, A corresponds to incident waves, and S is the scattering matrix. The term scattering basically refers to the fact that each incident wave on a port, incident wave on a port is scattered. That is, it is reflected or transmitted. Well, we have obtained the relationship for a junction of n transmission lines. Basically, it also holds valid for a junction of n number of waveguides. So this relationship B is S times A is also valid for a junction of waveguides. So that's all in this lecture. We'll be discussing the properties of S matrices or properties of S parameters in our next lecture. Till then, stay blessed.